In this video, we are going to continue talking about building mechanical assemblies. Specifically, we will talk about how to close mechanical assembly loops, set initial conditions for mechanical configurations, sense and log simulation results, add internal mechanics to joints such as stiffness and damping, actuate joints, and apply external force on parts. A simplified suspension system undergoing a force test is used to explain the various concepts. We will continue to build on the suspension system we built in part 1. Recall that we have already created the various components of our system, positioned them using rigid transform blocks, and specified degrees of freedom using Revolute Joint blocks. At the end, we saw an oscillatory behavior because it was missing a shock absorber-like component. In this video, we will add the shock absorber component and use a test platform to exert forces on the tire. Let's switch to MATLAB to see how we can do this. Let's open up a starter model shock absorber _ start. Let's update this model using the shortcut Ctrl D to bring up the Mechanics Explorer and switch to the right view. We see that it's the same model that we built in the previous video. Now let's add the shock absorber component. To do this, let's go back to MATLAB and open up shock absorber _ parts model. Let's update this model to take a look at the Mechanics Explorer and switch to the isometric view. Here we can see the shock absorber components already specified, namely the cylinder and the piston. We have already talked about creating components in the building components training video. So in this video, let us directly use these pre-built components to create our shock absorber system. To do this, let's go back to the model, select these two solid blocks, and copy them using the shortcut Ctrl C, go back to our starter model, and paste them using the shortcut Ctrl V. Let's create a shock absorber subsystem. To do this, right-click on the selection and say Create Subsystem from Selection. Let's rename the subsystem to Shock Absorber Subsystem and double-click on the subsystem to access its contents. Now, let's connect the cylinder to the upper arm and the piston to the lower arm. To do this, we need two connections from the subsystem. So let's rename the first connection to arm 1. Right-click and drag on this block to create a copy of it to create the arm 2 connection, and connect the arm 2 connection to the piston. Double-click on the arm 2 connection port to make sure that it lines up on the left-hand side of the subsystem. Select OK to save changes, and go back to the top level of the model to see that arm 2 appears on the left-hand side of the subsystem. Now, let's connect arm 1 and arm 2 connections to the upper and the lower arm, and bring up the Mechanics Explorer on the other side, and update the model. We see an error here. The error says model not assembled, position violation. Let's go back to the Mechanics Explorer here and switch to the isometric view. We can also see here that the part is not oriented correctly, and our lower arm also seems missing. This is because the arm 2 subsystem, which is the lower arm, is right now lying on top of the arm 1 subsystem. To see why this is the case, let's go back to our model and access the shock absorber subsystem. We see that we are asking SimMechanics to assemble the parts such that both the arm connections, arm 1 and arm 2, are at the same point. In this case, that is the center of mass of the cylinder and the piston. But physically, this is not possible in our mechanical configuration. Hence, the position violation error. In our block diagram, we are making the connections here that forces SimMechanics to try to coincide these frames. When creating closed loop assemblies like this, it is good practice to not close the loop as the first step. It is recommended to build assemblies incrementally from one end to the other. So for example here, let's go back to the top level of the model and break the loop by deleting the connection to ARM2. Now let's update the diagram. We see that the error has disappeared because we are no longer asking SimMechanics to make the connection at ARM1 and ARM2 at the same physical point. The lower arm also reappears. However, we can see that the shock absorber subsystem is still not oriented correctly. Let's fix this first. We will use a rigid transform block to rotate the cylinder about its y-axis by -90 degrees to orient it correctly. So let's go back to our model, access our Simulink library browser, scroll down to Simscape, and SimMechanics, second generation, frames and transforms to find the rigid transform block. Let's add this to our model by dragging this block into our system. Note that the rotation is going to be from the cylinder to the arm, so let's flip this block using the shortcut Ctrl-I. Let's rename our rigid transform to shock absorber to arm1 and connect it between the cylinder and arm1. Double-click on the rigid transform block to access its parameters. Let's rotate it by a standard axis. Since we are going to rotate it only by a single axis, we will use the y-axis and provide the angle as -90 degrees. Select OK to save changes, and let's update our diagram to take a look at the new orientation. Let's switch to the right view here and zoom in. We see that even though the shock absorber subsystem's orientation seems to be correct, the link between the chassis and the shock absorber seems to be at the center of mass of the cylinder. Instead, we need this to be at the end of the cylinder. This is similar to the positioning problem we had with the single link pendulum and the suspension arms in the previous video. We need to translate this component by half its length. In our model, we see that the cylinder's length axis is the z-axis, so we will translate along the z-axis. So double-click on the rigid transform block, access the translation components. We will translate by the standard axis method about the z-axis. We will move the cylinder down by half the length of the cylinder. Let's make sure we change the unit to centimeters. Select OK to save changes and update the diagram to see the cylinder move down. Now that we have specified the upper end of the shock absorber subsystem correctly, let's add a revolute joint between the cylinder and the chassis connection point here to define that this point can only rotate about the axis here. So let's go back to our model, open up the library browser, scroll down to the joints library to find the revolute joint, drag the revolute joint into our model, and let's connect this between the cylinder and the arm here. Let's go back to our Mechanics Explorer and update our diagram to take a look at the revolute joint here. In the isometric view, we can see that the z-axis of the revolute joint is pointing outward, which is the correct orientation for our revolute joint. Let's go back to the right view. Next, we need to take care of the piston. We need to connect the piston to the lower arm at a point here parameterized by the variable shock absorber distance. For this, we first need to create a frame at the end of the piston. To do this, we will use a rigid transform block again. Let's go back to our model, open up the Simulink library browser, go to Frames and Transforms, and add the rigid transform block again. We are going to specify the translation from the piston to the arm, so we can directly connect the rigid transform block here. And let's rename this rigid transform block to be shock absorber to arm2. Double-click on the rigid transform block to access its parameters. In this case, we are going to translate the frame by a standard axis. In this case, it is along the length of the piston, which is the z-axis, by half the length of the piston. Let's change the units to centimeters. Select OK and update our diagram to take a look at the new transform that has appeared here, shock absorber to arm 2, and we see the new frame at the end of the piston. Next, we need to attach a revolute joint at the end of the piston. To do this, let's go back to our model, right-click and drag on the revolute joint block to create a copy, and then attach it between the arm 2 and the piston. Let's update the model to make sure revolute joint 1 appears here. Let's also go back to the model to the top level and connect arm 2 to the shock absorber subsystem to close the loop, and update the model again to see if the configuration is set. We still see the position violation error. To debug this, let's break the loop again by deleting the connection between the arm 2 and the shock absorber, and let's update the model again. Let's zoom in and take a look at the revolute joint 1, which is the connection between the piston and the arm 2. We see that the z-axis is pointing down. However, for the base frame, which is the follower of the chassis arm 2 revolute joint, we see that the z-axis is pointing out. Let's go back to the right view. We need to align these two axes appropriately for the revolute joint. The correct orientation is for the z-axis to be pointing out. To do this, we need to rotate the frame at the end of the piston here. So let's go back to our model, access the shock absorber subsystem, and the shock absorber to arm 2 transform. Here we have only the translation specified. Let's specify the rotation as well. In this case, our base frame looks like this. Our follower frame looks like this. So let's specify the rotation as aligned axis method. When we align the axis, our follower x becomes the base z, and the follower z becomes the base minus x. Select OK to save changes and update the diagram. Let's switch to the isometric view and take a look at the follower of the transform. Now we see that the z-axis is pointing out, which is the correct orientation for our revolute joint. So when we take a look at the revolute joint, the z-axis is pointing out as well. So now that the axes are aligned, let's go back to our model to the top level and connect the arm 2 to the shock absorber and update the model again. The error still persists. It's still the position violation error. Let's go back to our Mechanics Explorer here and switch to the right view. Here we see the base and the follower axis of revolute joint 1. Even though the z-axis are aligned, they are not co-located. This is a requirement for the revolute joint. For these frames to be co-located, we need the piston end to be at the same location as the other revolute joint. So we need to translate the end of the piston to be coincident with this point here. This is not a positioning problem. On the contrary, this is an issue with us not defining enough degree of freedom for the system. For example, here the piston needs to be able to move up and down the cylinder. Right now, they are rigidly fixed to each other. We can verify this by double-clicking on the shock absorber subsystem. We see that there is no degree of freedom that is specified between the cylinder and the piston. We need to specify a single translational degree of freedom. We can do this using a prismatic joint. To add this, let's go back to the Simulink library browser, go to the joints library, scroll down to find the prismatic joint, and add it to our model. This joint allows the motion along the z-axis of the connected frames. In our case, the cylinder and the piston have their z-axis pointing down along their length, which is the correct orientation. So let's connect the prismatic joint between the cylinder and the piston. and update our diagram, we see that the piston moved down to be co-located with the other frame. So we can take a look at the Revolute Joint 1 to see its location. To complete our configuration, we need to move the piston along arm 2 by shock absorber underscore distance parameter that is specified in the suspension system parameters MATLAB script. For this, we will use the rigid transform block again. So let's go back to our model, open up the library browser, go to frames and transforms, and add a rigid transform block. This will be the transform from the arm 2 to the shock absorber. And let's connect this between arm 2 and the piston. Double-click on the block to access its parameters. In this case, we will specify a translation about a single axis, so we will specify the standard axis method. The length of arm 2 is along the y-axis, so we will specify this to be about the y-axis. And we can specify the offset as the parameter shock absorber underscore distance. Set the units to centimeters. Select OK to save changes and update our diagram to take a look at the shock absorber, which has moved to the correct location along the length of arm 2. Even though the shock absorber seems to be at the correct location, the wheel position seems misguided. Suppose we would like the wheel to be positioned lower for an initial state. Initial configuration like this for mechanical assemblies can be guided by providing initial conditions to necessary joints. In this case, it could be useful to specify an initial condition for the shock absorber piston's displacement. By doing that, we can control the wheel's vertical position. To do this, access the Prismatic Joint block by double-clicking on it and go to the State Target section. Here, we can specify targets for position and velocity. For our example, we will specify a position target, and let's specify a value defined by the parameter equilibrium position that is specified in the MATLAB script. Let's set the unit to centimeters. We see that there is a priority property which is set to high by default. In our example, we have only one initial condition specification, so the priority has no effect. If we had multiple high priority conditions, there may be conflicts, in which case we would see an error. Note that this is the same as the initial condition specification which we talked about in the Simscape fundamentals training video. Please refer to that video to get more information about this. For our example here, let's select OK to save changes and update our model. Now the assembly looks as desired. Recall that the status of initial conditions can be viewed by going to the Analysis menu, Simscape, and Variable Viewer. In our case, we specified the target for our prismatic joint's position, which we can see has been satisfied. Let's close this window here. Now that the assembly looks as desired, let's simulate the model. There are a couple of things we can notice here. First of all, we can see that the shock absorber is not limiting the motion of the arms. The system is still swinging like a pendulum. Let's right-click on the shock absorber subsystem and say Show Only This and replay the animation. Secondly, the shock absorber itself seems to be displaying the prismatic joint properties correctly. Next, we need to figure out why the shock absorber is not limiting the motion of the arms. While debugging models, in addition to observing animation of the simulation in the Mechanics Explorer, we can output values from a joint and sense physical quantities such as position, velocity, and acceleration about the joint's degree of freedom. Suppose we would like to measure the displacement of the prismatic joint to see the oscillatory behavior. Double-click on the prismatic joint block and access the Sensing section. In the dialog box, we can configure the joint to output various quantities as can be seen here. These quantities are sent out as Simscape physical signals, which can be used to graphically implement equations for physical components or effects. For our example, we need to sense the position, so let's select that and say OK to save changes to see the physical signal appear here. Now we need to convert the physical signal to Simulink signal so that we can visualize it using a Simulink scope. This conversion can be done using a physical signal to Simulink converter block. So let's go to the Simulink library browser, access Utilities under Simscape to find the physical signal to Simulink converter block. Double-click on the block to access its parameters. If a physical signal is converted to a Simulink signal, a unit conversion can be specified in the physical signal to Simulink converter block. So here, let's specify the output unit as centimeters. Select OK to save changes. Now, let's add a Simulink scope block. So go to the Sinks library under Simulink to find the scope block and add it to the model. Now, let's connect the physical signal from the joint block to the converter block and the output of the converter block to the scope block. Let's simulate the model again and double-click on the scope block to take a look at its output. We can see that the displacement seems to be undamped. So, the pendulum-like behavior is because the prismatic joint is modeled in an ideal fashion and doesn't seem to have any stiffness or damping specified. Also note that the signal looks a little jagged because we are using default solver options. If we used a different solver, for example ODE23T, we can see a smoother curve. Please refer to the documentation link in the resources section to get more information about this. Also, recall from the Simscape training video that depending on the number of signals we would like to access, we could alternatively use Simscape logging to debug, analyze, or post-process our model. This method does not add multiple blocks like scopes and converters and hence reduces model clutter. Refer to the Simscape training video in the resources section to get more information about this. Now, let's add stiffness and damping to our prismatic joint to take into account the real-world mechanic effects. Let's double-click on the prismatic joint block and access the internal mechanics parameters. Here, we can specify equilibrium position, spring stiffness, and damping to model the internal mechanics of the joint. So in our case, let's specify these to be the variables specified in our MATLAB script: equilibrium position in centimeters, spring stiffness Ks, and damping coefficient ds. Select OK to save changes. Let's bring up our Mechanics Explorer as well. Let's right-click on the shock absorber subsystem and say Show Everything and update our model. Now let's simulate our model with real-world mechanic effects implemented. We see that the wheel just slides down a bit and the shock absorber extends under gravity. This is the expected behavior for our model under only the force of gravity and no other external forces. We can verify the effect of stiffness and damping by double-clicking on our scope block. We can see that the signal is damped now. The prismatic joint settles to a steady-state position. Let's go back to the presentation and do a small recap. We started by adding the shock absorber part to our existing suspension model. We saw that it was not aligned properly and needed to be transformed using a rigid transform block to be positioned correctly. Next, we implemented the degrees of freedom. We added Revolute joints at the links connecting shock absorber to the upper and the lower arm. We also saw that the frames did not align correctly and had to rotate the frames to align for the Revolute joint. We used rigid transform block to align the frames. Next, we wanted the piston to be able to move with respect to the cylinder. So we specified a prismatic joint to do this. We also saw that our frames were already aligned with the z-axis along the prismatic degree of freedom, so we did not have to do any corrective transformations using rigid transform block. Next, we introduced the concept of specifying initial states for joint variables to guide initial mechanical configuration. We specified the equilibrium position as the initial state here. Recall that this is similar to the initial condition specification in Simscape that we discussed in Simscape Fundamentals training video. Next, we simulated the model to see that the system was still in an oscillatory state. We explored this by sensing the position of the prismatic joint and plotting the result on a Simulink scope. We also noted that the Simscape Results Explorer works with SimMechanics as well. We talked about this in the Simscape training video, so please refer to that in the resources section to get more information about this. We then rectified the oscillatory state by specifying internal mechanics for the joint. We specified equilibrium position, stiffness, and damping coefficients to see that the system settled to an equilibrium state. All along, we have been testing our model only under the force of gravity. Next, let's add external actuation to our model. We will use a test platform and exert force on our tire. Let's switch to MATLAB to see how we can do this. Let's open up a starter model, shock absorber force test _ start. Let's update this model using the shortcut Ctrl D and switch to the right view. This model is the same as the one we just built, except for two additional components. The first is the test force subsystem. This subsystem places the test platform at the particular location that we have specified here. We have already covered how to create solids and position them using rigid transform blocks. The second addition is that we have an extra frame created at the tire contact point. We are going to assume that the contact point is always fixed at this position and can only move in a planar fashion. Next, to exert forces on this contact point using the test platform, we first need to move the test platform. We can do this using joint blocks. In our example, suppose that the platform is restricted to only a translational motion in one axis, that is the vertical z-axis of the world frame. We can implement this using a prismatic joint. So let's go to the test force subsystem. Let's add a prismatic joint by going to the Simulink library browser, scroll down to our joints library, find the prismatic joint, and drag it into our model. Let's add this between the world and the platform here. Double-click on the prismatic joint to access its parameters and expand the actuation section. Here we can see several different actuation configurations. We can select automatically computed for motion and set force to be provided by input. When we select apply and go back to our model, this will add a physical signal input to the prismatic joint block labeled with a lowercase f. Let's go back to our prismatic joint. This actuation mode is called forward dynamics. Alternatively, we can select the motion profile to be provided by input and the force to be automatically computed. Select apply and go back to our model. This will add a physical signal input to the prismatic joint block labeled with a lowercase p. Let's go back to our joint. This actuation mode is called inverse dynamics. In our scenario, we are not really interested in the forces required to move the plate. Rather, we would just like to move the platform with the provided motion profile. For example, we could just imagine the plates to be simulating bumps on the road. So, we will set the motion to be provided by input and automatically compute the force required to get that motion profile. Select OK to save changes. Let's create a pulse generator signal as an example input motion profile to apply here. To do this, let's go to the Simulink library browser, access the sources library in Simulink, and find the pulse generator block. Add it to our model. Double-click on the block to access its parameters. For our example motion profile, we will supply a signal with the amplitude of 5 centimeters. So in this case, it's 0.05 meters with 2 seconds period and a square wave. So we will select the pulse width to be 50% of the period and select OK to save changes. Now, this is a Simulink signal and needs to be converted to a physical signal to be fed into the joint block. To do this, let's go back to our Simulink library browser and access the Utilities library under Simscape and drag in the Simulink to physical signal converter block. Let's connect the pulse generator to the converter block and connect the output of the converter block, which is a physical signal, to the prismatic joint. Double-click on the converter block to access its parameters. We are going to use default input signal units. In this case, that's going to be meters. Notice that there is another tab here called Input Handling. To avoid solver errors, it is recommended that we provide the first and second derivatives, that is, velocity and acceleration of a motion profile. Input filtering makes the input signal smoother and generally improves model performance. There are a couple of ways here to do this. We can use the filter input method to take filtered derivatives of the position signal that is supplied to the Simulink to physical signal converter block. In this case, the blocks take care of the input filtering automatically for us. The second way is to provide our own input derivatives. These could be generated, for example, by using custom transfer function blocks. We can choose either of these methods based on the way in which we want to filter the input. In our example, we will use the filter input method and use second order filtering and use the default time constant that is specified here. Let's select OK to save changes and go back to our Mechanics Explorer, update our diagram, and take a look at the test for subsystem. We can see the prismatic joint here. Let's simulate the model. We can see the platform move up and down. Note that there is no effect on what the tire does with respect to the platform. This is because we have not yet modeled the force interaction between the platform and the tire. This is our next task. First, we need to establish the degree of freedom between the tire contact and the platform. We can again use the prismatic joint here and restrict the motion to only the vertical axis. We can also use a planar joint to give it 3 degrees of freedom, which is displacement across the y and z of the world frame and the rotation about the x-axis. To do this, let's go back to our model, access the Simulink library browser, and go to the joints library to find the planar joint. Let's add this to our model and connect it between the platform and the wheel. Now, to exert forces on the wheel from the platform, we can think about actuating this planar joint using force in the forward dynamics mode. However, if we take a look at the wheel and the platform, the force is always applied vertically upwards regardless of the rotation of the tire. This is why the force relationship between the platform and the tire is not easy to capture using joint blocks. To exert force on any frame regardless of joint blocks, we will use the external force and torque block. Go to the Simulink library browser and under Sim Mechanics, go to the Forces and Torque library to find the external force and torque block. Let's add this to our model and rotate it using our shortcut Ctrl-R. This block can be configured to apply force to any particular coordinate frame, whether a joint is attached at that particular location or not. Double-click on the block to access its parameters. So in our case, we need to actuate it using force. And in our Mechanics Explorer, we can see that that force needs to be about the z-axis of the world frame. So let's select force z and the force resolution frame as the world frame. Select OK to save changes. We can see an input force Fz which needs to be computed based on the motion of the platform, and the port F is going to be the attached frame to which the force will be applied. To compute the force Fz based on the motion of the platform, we need to measure the displacement and velocity between the platform and the wheel. We can do this using a transform sensor block. So let's go to the Simulink library browser and go to the Frames and Transforms library under Sim Mechanics to find the transform sensor block and drop it inside our model. This block can be used to sense various quantities between any two frames. In our case, we will connect the base and the follower of the transform sensor to the base and the follower of the planar joint block, which describes the relationship between the platform and the tire. Double-click on the transform sensor to access its parameters. As we can see, there are several properties that can be measured using this block. The measurement reference frame can be set to one of several options, as can be seen here. For our example, we will leave it to the world frame. Now, we would like to measure the translation along the world z-axis and the velocity along the world z-axis as well. Select OK to save changes to see two more output ports appear, which gives us the translation and the velocity along the world z-axis. Now, based on the position and the velocity that we have measured here, we need to implement a hard stop-like mechanism. We will use fundamental Simscape blocks to do this. Let's go back to MATLAB and open up shock absorber _ calculate force. This model has a subsystem built specifically for our example. Given z and vz, it computes the force. Inside the subsystem, we can see the graphical implementation of the equation. We will implement the force equation kw times z plus dw times vz if the measured distance is greater than 0. Otherwise, we will apply zero force. This is the hard stop-like mechanism. Let's go back to the top level of the model and copy the subsystem by using the shortcut Ctrl+C. Go back to our starter model and paste it inside our subsystem here. Now, let's connect our subsystem to the output of the transform sensor and connect the external force block to the output of the calculate force subsystem. Let's also connect the external force block to the frame to which it needs to exert the force on to complete the connection inside the test force subsystem. Let's go back to the top level of the model and make sure that the test force subsystem is connected to the contact point in the wheel. Let's bring up the Mechanics Explorer to the other side and update our model and switch to the right view here. Let's simulate the model. Now we see that the tire moves along with the platform. Looking at the planar joint, we can see that the frames are moving with respect to each other. Since we are modeling contact between only 2 points in the rigid body, we see some overlap between the two solids. We could make our force calculation more sophisticated to correct this overlap if we model the contact as a surface instead of a point. Let's go back inside the test force subsystem. Recall that we are using a Simulink source block to actuate the platform itself. This can be changed to any user-defined input. For example, let's go back to MATLAB and explore the variables position time and position right wheel and plot them against each other. This is an example motion profile. To subject the platform in our SimMechanics model to this motion profile, we can use an input port block from Simulink. Let's go back to our model and open up our Simulink library browser. Let's scroll up to access the sources library and find the input port here. Let's go back to the top level of the model and add the input port. Let's rename the input port to motion profile. Let's copy this input port using the shortcut Control C. Access our subsystem by double-clicking on it. Let's delete this Simulink source block and replace it with our input port. This port will act as the subsystem interface to the top level of the model. So let's go back there and connect our input to the subsystem. This port is a root level input port and can accept data from the MATLAB workspace. To configure this, open the configuration parameters by clicking on the gear icon. Here, select the Data Import Export pane. Check Input to be loaded from the workspace. And here, we will specify the MATLAB variables that correspond to the time vector. So in this case, that is position time. And the input vector, so in this case, that is position right wheel. Notice also that our data runs till 60 seconds. So let's change the simulation time. So let's go to the solver pane and change the stop time as the last element of the position time vector using the end keyword. Select OK to save changes. Let's bring back our Mechanics Explorer. Let's update the model and simulate the model to see the suspension system going through different motion profiles and undergoing an external force test. We can go inside the shock absorber subsystem and take a look at the scope to see the displacement of the shock absorber for the various force tests that we are performing here. We can measure all sorts of parameters like constraint forces to further analyze the dynamics of our system. Let's go back to the presentation and do a recap. We wanted to actuate the test platform. We discussed a couple of ways to do this using the joint block. We can either provide force as input to compute the resulting motion, a mode called forward dynamics, or provide the motion profile as the necessary input to compute the force that is required to get that motion, which is inverse dynamics. For our application, we just wanted to move the plate given a motion profile and were not interested in the forces, so we chose the inverse dynamics mode. We provided the input through a Simulink pulse generator block. Note that user-generated waveforms can be imported a variety of ways into Simulink. Please refer to the documentation link in the resources section to get more information about this. We also used a Simulink to physical signal converter block. To avoid solver issues, it is recommended that we provide first and second order derivatives. We discussed a couple of ways to do this, using a second order filtering at the input, which is the approach we used, or we could manually generate and feed in the derivatives as shown here using integrators or transfer functions. At this point, we saw the test platform move up and down. However, there was no interaction between the platform and the tire. To implement this, we established a planar joint between the platform and the tire. Then we discussed how there may be situations where we would need to exert force on a particular frame regardless of whether a joint is available at the position or not. This was one of those scenarios. So we used a transform sensor block to sense the vertical translation and velocity. We fed this to a graphical equation implemented using Simscape blocks to compute the force to be applied. We then configured the external force and torque block to apply the computed force in the vertical direction of the world frame. We then simulated the model to see the effect of the test platform on the tire. Note that this is just one way to model contact forces. Please refer to the link in the resources section for other ways to do contact modeling. This includes references to modeling hard stops, penalty formulation with Simulink, and a custom contacts library. In summary, we talked about closing loops for mechanical assemblies, setting initial conditions for mechanical configurations, sensing and logging simulation results, adding real-world mechanics into simulations such as stiffness and damping, actuating joints based on motion profiles and forces, and finally, we saw how to exert force on specific frames independent of joints. This concludes this video.